A novel development of a biodegradable face mask. There's an insanely high demand for disposable face masks due to COVID-19, and this increase of disposable PPE use has resulted in improper disposal of this equipment, making it a new source of pollution. Because of this, there is a need for efficient, environmentally sustainable, biodegradable face masks. Our main research question is, will a biodegradable disposable face mask using gelatin-based bioplastics be as effective in blocking particles as those on the market? Our hypothesis also states that if specific quantities of glycerol, gelatin, and water are mixed into a bioplastic, then a thin, biodegradable, flexible plastic sheet will be produced, and when associated with a filter into a face mask, it will have a 90% particle filtration rate compared to highly regarded N95 masks or surgical masks. Our objectives include making a bioplastic sheet and converting this sheet into a fabric-like material, which assembles into a face mask that will be tested with efficiently with little particle penetration and thickness, yet have high breathability and flexibility. Our materials include materials to make the biodegradable to make the bioplastic, materials to assemble the face mask, and lastly, materials to test the efficiency of our mask. Notable materials include glycerol or glycerin, cornstarch, gelatin, water, and materials to assemble the bioplastic include a clothing iron, which would be used to iron the parchment paper and the resulting bioplastic. A canvas, coffee filters, 100% pure beeswax to make it water resistant, sewing machine, beads, metal wires. And testing materials would include food coloring, spray bottle, cardboard box, rubber bands, water bottle, ruler, hair dryer, and a candle. And lastly, we'd have materials to dispose, such as kitty litter.
And protocols. Assembling. The first step in our procedure is to combine glycerin, water, and gelatin or cornstarch. After combining these ingredients, the next step is to flatten and mold them into a rectangular shape and allow them to dry. Next, we'll iron over the plastic to make it fabric-like. At this point in the procedure, we'll have 3 layers that will make up our mask. 2 bioplastic layers surrounding a filtration material that is to be tested based on their individual efficiencies. After this, we'll apply a waterproof wax to the outer and inner layers to prevent the formation of water droplets. Finally, we'll assemble all the parts together by sewing them or hot gluing them. These are some images of our procedure. In the first image, we added all of our ingredients into a pot. Following this, we mixed them together, and then after this, we heated them up so that the consistency changed. Finally, we flattened out the bioplastic onto a baking sheet and allowed it to dry. Procedure and protocols. Testing. Testing the bioplastic's particle filtration efficiency. To test the particle filtration efficiency, we'll mix 50 to 60 milliliters of water with 3 to 4 drops of food coloring into a spray bottle. Protocols. Testing. To test the filtration efficiency of the bioplastic, we will create a solution of 50 to 60 milliliters of water with 3 to 4 drops of food coloring into a spray bottle. We will orient this spray bottle onto the inside of our mask, and we will spray it and record the number of particles that escaped onto a blank sheet of paper at various distances from the mask. To test the breathability, we will keep a lighter various distances from the mask and orient a hair dryer on the inside. We'll record the distance at which the candle is blown out.
We will test the flexibility, fabric strength, and thickness of the bioplastic. For testing the flexibility, we'll first cut out a hole in the base of a cardboard box, then flip the box upside down and place the fabric over the hole with an empty water bottle on top. Lastly, add 10 milliliters of water into the bottle until the fabric bends in, and then record the weight of the water bottle at the point. As you can see on the bottom left, the pictures show the procedure for the control and the bioplastic. For testing the fabric strength, we'll first attach the rubber band on a hook and loop the mask around the other end of the rubber band. Then pull the mask until it breaks and record the length of the rubber band at the point at which this happens. To limit variability, rubber bands must be consistent in size and new each time. Lastly, to measure the thickness, we will simply use a ruler, as shown on the picture on the top left. We created tables to show the breathability, flexibility, and thickness of surgical masks and bioplastics. On the top left, the data table shows the distance a candle can blow out for both masks and show that the average distance for surgical masks is 3.5 inches, while bioplastic distance is slightly smaller at 2.7 inches, which shows that the filtration of the bioplastic is similar to that of the control. As for the thickness of the bioplastic, the table on the top portrays that the thickness of our bioplastic is 1.5 millimeters thicker than our control, which can account for the slight decrease in the breathability of the bioplastic. On the top right, the table depicts the flexibility for both the control and the bioplastic. As you can see, the control was only able to hold 90 grams of water before it broke through, while the bioplastic can hold up to 110 grams, which shows that it is more durable and slightly less flexible than the control. Lastly, while we are unable to find the particle filtration efficiency of the bioplastic, the graph on the bottom depicts the particle filtration of our control, or the 3M1826 face mask, as it has around 75% particle filtration efficiency. As we conducted tests, our data proved that our bioplastic was similar to our control in terms of flexibility, breathability, and thickness, and using this we can infer that our mask will have a comparable particle filtration efficiency. Although the bioplastic's breathability is slightly less than the control, it is similar. In the future, we plan to test the amount of reactants needed, assemble the face mask through fabric, ironing, beeswax, and ear loops, and implement the remaining tests. However, despite these limitations, our mask has environmental and health applications. Firstly, since our mask is biodegradable, it benefits the environment as it can reduce the plastic footprint from mask pollution. Additionally, it would have an impact on the well-being of the community, as we aim to have a 90% particle filtration efficiency, which is greater than masks on the market. In the future, we hope to embark on projects relating to biodegradable medical implants, as well as comparing the efficiency of various masks either through using a light scattering method or through analyzing the length of bacterial life on masks.